Assalamualaikum, Bismillahirrahmanirrahim. Yes, hello everyone, how's it going? So today we will be checking our final chapter in Chemical Process Safety book, which is chapter number 12, which talks about risk assessment. And last time we have taken chapter number 11, which was talking about the hazards, and we talked about the hazard studies, and which is the hazards and operability study. And we also talked about the hazard surveys, the DO index, and we have spoken also about the safety reviews, which group of people sitting together and discussing after they get all the information about the process, and they suggest some kind of changes, relying on the consequences that they would expect for that plant. And we also had taken some one of the other methods, which was the what if analysis, the guy who always searches for problems, right? So that was it for chapter 11. And chapter 12, it's just a continuation of what we have taken, because it's still more like qualitative, how we look at risks and looking at the areas where there could be some problems. And in this case, we want to look at the areas that we could have high risk and some other methodologies that we could go through. Okay, so risk assessment includes an incident identification and the consequences. So how an accident occurs, and you analyze its probability, and what are the consequences. And we always represent that like this is like talking about is probability. Mainly you're talking about the frequency, like how many times does it happen? Does it happen every day? Does it happen every month? Does it happen every year? And the consequences, like is it dangerous or not? And how do we calculate this? Usually when we multiply our frequency with how much dangerous is something, and then you're going to say, well, if it happens every day, right? It happens every day, and it is very dangerous. That is something severe that we never want. But for example, it happens every year once, but it is very dangerous. Of course, this will be still a risk, but it will not be as high as if it happens every day. Now, if it happens every 10 years, and it's very dangerous, and here every 10 years and very dangerous, is just puts the risk really very low because it happens every 10 years. Now if you say it happens every 100 years, forget about it, right? So the thing is that the frequency it will increase the risk. Okay, will increase the risk if it happens every and then. So every now and then, if it happens, it's very risky. What about the dangerous part? The dangerous part is that it may happen every day, but it is not risky at all. It is something that is not dangerous at all, which means that could be we don't need maybe a design for that to be inherently safety, but we just deal with this. We just deal with it. So now I just said that it's not that risky. Why? Because I just said that it's not dangerous at all, even if it happens every day once. And now if it happens every 1 hour, will this be accepted or not? Now if it happens every 1 minute, I know this is crazy, but what I'm trying to say that when I say it's dangerous and now I increase the frequency, I think it becomes dangerous in this case. Okay, so this is the risk where you multiply by the frequency and what are the consequences, right? The frequency and the consequences are how much it is dangerous. So, and frequency is telling you that how much it happens per certain time. And if you have a high risk, you will say, for example, it is in the category A where it is unacceptable, and then category B where it is, for example, critical, and then you have serious, marginal, negligible. Okay, and these are different from different places, so it always depends on what place you're talking about. If I'm talking about a university, it's different when I talk about an industry, right? And it's different when I talk about my shop. that sells hamburger. So everyone has its own different risks. We are going to add something. So usually this is, you will not find it in many places, because they consider this as one. I mean, they more concentrate on the frequency to consequences. But operational discipline is something like you're adding, if you have a bad safety precaution, you don't have good management for safety, no procedures. So you're putting this down, and this just increases the risk. Okay, this just increases the risk. But I will talk that you have good procedures, really very good procedures, to deal with all what you have, right? So that what will happen here to the risk will go down. Okay, so that is the operation disciplines. How much you are ready for those risks? How much do you have in system, management wise, and procedures, and even the instruments, the sensors, the safety precautions, and so on. So what is the operational discipline? The personal commitment of everyone to ensure their personal and process safety by performing their tasks, so everyone knows his task or knows her task, recognizing and responding to seeking help to anticipated situations, so they know what to do when they have some kind of situation conditions. Sometimes also operational discipline is reflected as a leadership focus, employee involvement, practical, consistent with you have good procedures, excellent housekeeping, awareness, knowledge, commitment at the personal level. So that is at the organization personal level. So I think so you got an idea about OD. Of course, if you ask me what is the value of OD, always keep it as one. Because it's very difficult to identify that. Only if you have at your industry something that you can identify what is the value of OD, that is going to be different. Okay, we already explained part of that, and this is where I explained that if operational discipline goes low, the risk goes high. And this is just an example very quickly. I have any examples in my head, but it just says that if you have a very high frequency, and very high frequency usually in your head, it's like once in every 2 years. High frequency once in 10 to 50 years. Moderate frequency event not expected in the lifetime of the plant. Okay. Low frequency event known to us, just to know it. So this is just numbers just tells you about what time dimension I'm talking about. Okay, so that is the equation. That is the equation that we have, and our PSM, process safety management. They are, if you compare the risk reduction efforts and evaluate it against potential business risks, and the risks we are talking about here. It could be environmental, operational, maintenance, quality, and financial. So there are many kind of risks. So it's not only risks to a person, but there are many kind of risks. And if you go to the process safety management and read about it, you're going to see the different risks that are incorporated in that standard. So that was the first part, just to get an idea about what is risk and how to calculate this. Now getting to a different view of it. Okay, so what I had explained was something very generic. Well, if you go to industries, there are more detailed definitions in this regard, and the definitions that you have in industry is something called reliability. Okay, something called reliability, this word here, it's very popular. And there have been studies like master studies and to talk about reliability and how reliable is this industry. So you can go to a certain unit that you have in the plant, and then you're going to calculate the reliability. So what is reliability? It depends on the probability. Okay, it depends on the probability. So that is where it concentrates. So what is it? Let me go more into details about it. Equipment failures or faults in a process that occur as a result of a complex interaction of the individual components. So what I'm talking about failures. How much does this happen? Does it happen every year? How many equipment failures I have? For example, I'm talking about valves. how many failures I will have per year for valves. What about compressors? How many failures I will have in my compressors per year? So if you have, for example, compressors think that it is 0.1, and then you go to valves, it's 0.8, for example, or for valves maybe it's like 2.5. You will say that all the valves, they fail much more than the compressors. Okay, the valves fail much more than the compressors. Why? Because I can compare what? I can compare the equipment failure here, frequency or the probability. The data are collected on the failure rate. So we collect data to know that how much does it fail. Okay, but we already know from previous experience. But if you don't know, you can collect the data and see how much it fails. The component fails after a certain period of time. Okay, so you already mentioned that. This is called the average failure rate, and it's represented by mu with units of faults per time. So we calculate this failure as faults per time. The probability that the component will not fail, which is the opposite, it is given by a Poisson distribution, and this is our kind of distribution, but not to go to the details of it. This is the way how we calculate reliability. Okay, so the reliability, which is something good, it is the exponential to the negative of mu, which are the faults per time. How many faults, how many failures I have per time? T. Okay, so this is the exponential of minus failure. Gives me the reliability. Now, if I want to calculate the failure probability, which is the unreliability, which we represent as P of T, it is equal to 1 minus the reliability, 1 minus reliability. So if something that is only 0.1 reliable, that is not very much reliable, right? So if it's only 0.1 reliable, what is the probability of failure? The probability of failure is very high, which is 0.9. I hope you got the idea, right? So the lower the reliability, which is something good, it's not good. And of course, this is reflected very clearly when we say failure probability, that is 0.9. Okay, failure probability. Think of it as a percentage, 90 times per 100. So the probability that we'll have failure from 100 cases are 90. So that is a very high probability. So if failure probability is 0.5, so it's 50%. So that is the meaning of failure probability. And these are opposites, right? Reliability and failure probability, they are the opposite each other. So this is how we calculate. All we need is mu. We calculate reliability, and from reliability we can calculate the failure probability. Now it can get complex. And in this case, I'm just showing you of the complex cases that we have. And this table, you always need to keep it in front of you, because it's going to be very supportive when you try to solve some problems in this chapter. Well, what do we have here? If we have, this is the failure probability first, which is P, right? This is P, and here's also P. Here's the reliability, which is R, and here's the failure rate, which is mu. So if I start with the failure rate, which is mu, how many times per year? So if I have two failure rates, this could go fail, and that could fail as well. For example, you have two valves redundant to each other. So it could be this and this, right? Or that. And since that we have this failure rate, if you have something redundant, actually you're going to add them. And it's not, maybe not the redundancy, more than that you have, for example, a valve, or you have also an alarm system here. So this could fail and this could fail. Now, this or this, they are independent of each other, but the total mu will be mu1 plus mu2. So you add the failure rates. That you have. However, if you have the AND, in which both of them could happen together, they are very much related. There's a different equation in which you can calculate mu, which is minus ln r divided by t. Okay, minus ln r divided by t. How did we get this equation? I mean, I will not go through the details. It's simple, it just comes from the e to the power minus mu t, and you're trying to put your reliability equal to 0 and finding mu. Okay, so that is the only idea if you want to do your math there. Okay, what about now the reliability? After I get the mu, if we have an OR gate, okay, we have an OR gate, so this or this happens, they are independent from each other, not depending on each other, so you multiply the reliabilities. What do? You multiply the reliabilities, and that is the idea. So you multiply the reliability. So this is just a generic thing. And now to get to get this failure probability, if you can recall, what is reliability? Reliability is failure probability is 1 minus r. So it's 1 minus r1 into r2, and that is written here. 1 minus r1 into r2. So after you do your math here, you're going to get some generic thing here. So you calculate the reliability and then you calculate the probability. So if things are in series, you see here it's written if things are in series, what you're going to do, you're going to multiply them. So if in talking about reliability, you multiply them, and of course this equation depends on what? Depends on that. So you multiply them. And if things in parallel, now you're going to go to the failure probability. You multiply them if in the failure probability, and the opposite, you're going to write that if they are in series. So the failure of the system requires the failure of both components, right? So the failure of the system requires the failure of both components. So both of them should fail for that R to be failing. I don't know if you recall from probabilities where you add them or multiply them. It all depends if they are dependent or independent of each other. Note that there's no convenient way to combine the failure rate. So what we're trying to say here, this is the way that we can have things. If we have things in series or in parallel, where you can calculate the failure rate, the reliability, and the failure probability. Okay, great. Just to know the values of mu that we have. So the values of mu that we have, which are faults per year. So these are how many faults per year we have. So what do we have? Just to get an idea, we need a comparison here. So control valves is 0.6 faults per year. So we are talking about how many faults? We are talking about every 2 years you're going to have about 1 fault. For control valves, like every 2 years you're going to have more than 1, 0.6 and 0.6. So that's 1.2. You're going to have 1. So this is what you're going to say. Wow, every 2 years I'm going to have only one fault. Yes, but if you have 1,000 control valves, now how many faults you're going to have per year? Oh my God! Now I'm going to have 2,000 faults per year, right? Per 2 years. And that is about 1,000 faults per year. So I'm going to have every year 1,000. And now if you think about 1,000 per year, now your head is going to click and say, oh my God, that's too much. And why it's becoming too much in this sense? It is becoming too much because if you think about per day, divided by 365, you're talking about every day you're having a fault in a control valve. So this is when you start putting things in numbers, you find out that it may become much more complicated. Okay, let me get that. So again, sorry for that. So what do we have here? We also have we want to compare the flow measurements for fluids and flow measurements for solids. Solids, if you have a flow of solids, you always have failure much higher than the ones of a fluid. Why? Fluid is much more smooth. This one blocks and causes some problems. A gas liquid chromatography, we always have. I don't know if you dealt with that, but I dealt with it, and it's crazy. If you have a chromatography at your lab, you see how many faults per year. It's 30.6 faults per year. So you're talking about like every 10 days you're having a fault. And that is true. We always have a problem and call the technician. The technician comes. What problem do you have? I just fixed it 1 week or 2 weeks ago. It's written there that these are the numbers of faults per year. We are expecting to get something like that in our life. So they are very important, but they have a lot of faults and so on. There are things which are very less of faults, like the pressure relief valve, because it is the least of in contact of our process and system or chemicals, and that is why it has the least of it. Just to take an example, so this is like an example. Both systems demonstrate unrevealed failures. For the alarm system, the I just went for the solution. So this is example 2.3. So let's go to example 2.3 and find out the problem. So before we get to example 2.3, there's one problem I think so that is good to solve, which is example 12.2. And in this case, what do we have? We have a diagram, and this is the diagram that we have where it's just a reactor. We have a stirrer, of course a chemical reaction, and we are having some kind of a switch here, and it's written A. We have an alarm set at a certain pressure value. We have a pressure controller here, indicator of course, and a controller, and we have a solenoid valve sitting here. So what is the reliability of that system that we have here? Okay, so this reactor contains a high pressure alarm to alert the operator if we have any dangerous thing, and of course we have a pressure switch, and as we said, we have an alarm light indicator, and on the other side, for additional safety, I have an automatic high pressure reactor shutdown system is installed. This system is activated at pressure somewhere higher than the alarm system and consists of pressure switch connected to a solenoid valve in the reactor feed line. The automatic system stops the flow of reactant. So it stops the flow of reactant in any dangerous pressure, if there's any dangerous pressure. Compute the overall failure rate, the failure probability. Overall failure rate, again, the failure probability, the reliability. So we want mu, and then we want P, and then we want R. And then the mean time between failures. Okay, we did not take them, but that's simple. And we are going to assume by the problem here 1 year of operation. So what do we have here? This is what we have. So now we are going to include our switch alarm and the switch for the controller here, and the solenoid valve. So this is what we have: pressure switch 1, alarm indicator, pressure switch 2, solenoid valve. And from the table, we're going to see that for switches, this is the faults per year. For alarms, this is the faults per year. And for solenoid valves, these are the faults per year. So these are the faults. To calculate the reliability, we just take the exponential term, and we calculate the reliability of each one. And here you can see which one is more reliable. So for example, the alarm indicator is more reliable than the rest because it has a less faults per year, okay, less mu. Now if you want to calculate the failure probability, which is the other way of looking at it, we just subtract by 1, and of course you're going to see the one which has the least failure probability is that. So this is 0.04, giving you the idea that has least failure probability. Now I want to look at a system as a whole, right? A system as a whole. What is the reliability of that system? And then what do we have here? You can see that these things are in series, these two are in series, but this is in parallel with that. Okay, so I know that these two are in series, but if you can see that this is parallel with that. Okay, so these two, like, they are parallel. So in this case, I'm going to calculate the R for each one, and then I multiply them, right? I'm going to multiply them, and I'm going to calculate the R for each one, and I'm going to multiply them. And after I get the reliability of these two systems here, what I'm going to do, because they are in parallel, now I need to go to the AND OR system that I have found out, and this is equal to 1 minus the R3, I think so it was like that, 1 minus R3 into 1 minus R4. So something like that if they are in parallel. Okay, so this is what we'll try to do. So the first thing we are going to start because they are in series and it's written here, these two components are in parallel. The two components, I mean on the right and the left. For the alarm system, the components are in series. So R is equal to 0.87 to 0.96. So you multiply them. You multiply 0.87 to 0.96. And you get the value. And of course, the failure probability is 1 minus R. That's the answer. And mu is minus ln R. We can calculate how many faults per year for the total, right? This is if we said that they are in series, right? And what is the mean time between failures? You just divide it. 1 divided by mu, you get how many, what is the mean time between failures. So from one failure to another failure, it is 5.56. Now for the shutdown system, which gets into being if that thing is not working, and I mean if that thing it happens that it could not withstand what is happening. So again we multiply them, they are in series, the solenoid valve and the alarm. So you multiply 0.87 into 0.6. So you multiply them and then subtract them from 1 to get the failure probability, and then get mu, which is minus ln R because they're in series, and you get the mean time between failures. Now the two systems are what? The two systems are in parallel. So now we're going to go to the P part because it's easier, and we just multiply them because they are in parallel, and we get 0.07. And by that we can calculate the reliability, which is 0.93. And you can see that is really good. 0.93 reliability is really good. If you want to calculate the failure rate, which is minus ln R, in the case that they are in parallel, and you're going to get 0.073 faults per year. I can't understand this in years, so I need to calculate the mean time between failures, and I get a 13.7 year. Now I understand that this will one fault will happen every 13.7 year. So it's beautiful to look at it, right? It's just nice to calculate these numbers, and it gives you more confidence in terms of numbers that things will happen or will not happen. Okay, so that was 12.3. I saw that was 12.2. Now going down to 12.3. There are more equations here, but I did not take these. Don't worry about them now. Was it 12.3? I think that I solved 12.2. That was what meant to be then. Then I just solved 12.2, which is the example that we wanted to solve actually, because this part that I will not cover, which talks about availability and unavailability for both the alarm and the shutdown system. There's something called availability and unavailability. I did not take that, and it's just to keep easier things for you. I just decided that I will not cover that. So here I think so we meant that we have example 12.2 rather than example 12.1. So going to the next section, after knowing the failures and the probabilities, we have the event tree. So it's another way of how to know where do we have a high risk, and where we can know that we have a high frequency of what you're trying to see here. And the way that we can see the event trees, I mean, it comes from the word trees and events, right? So that there's an event, but it's a it's like one event is a consequence of another event. So it's like series of events, one event after another event. So event trees begins, of course, with an initiating event, which starts everything, and then it works towards a final result. And then, of course, you can go backwards. If you have the final results, you go back to the initiating event. Imagine that you do this by hand and you discover, or not that discover, that you already know what final result you will achieve if you have the event trees of many initiating events. So something that you do as an assessment to assess where do you have your risks. So this approach is inductive, so you do it before in hand. The method provides information on how a failure can occur and a probability of occurrence. So we want to know how a failure can occur by knowing the events of that. So the typical steps of any tree analysis is what? Identify the event. What is the initiating event, where it starts? And then what are the safety functions? We identify them, designed to deal with this event. we construct the event tree, and then we put we describe the resulting results, accident, event sequences. What are the accidents that could happen? So what do we need? If we have data, of course, the procedure is used to assign numerical values to the events. You put numerical values, and we're going to see that in a moment. This is used effectively to determine the probability of a certain sequence of events. So an example here, we directly go to an example in 12.8, and actually the example here, let me see. So that is the example that we have here, 12.8. So we already know this example. We have went through it many times. A reactor, we have cooling, and we have, of course, water going outside. And in this case, what do we have? We have a temperature controller, and it has an alarm as well. We have a temperature controller to make sure that if your temperature goes up because of the exothermic reaction, you're going to have more cooling water in. Okay, so what do we have? A high temperature alarm has been installed to warn the operator of high temperature within the reactor. The event tree, now we want to start the initiating thing, right? The event tree for a loss of coolant initiating event is shown in figure 12.9. So we have no cooling for some reason. 4 safety functions are identified. These are written across at the top of the sheet. So here it is explaining to us what is happening. The first safety function is the high temperature alarm, okay, because the temperature is going up. The second safety function, the operator noticing that there is a high temperature alarm. The third safety function is the operator is re-establishing the coolant flow. He's correcting the problem, okay? So the operator is taking action. The final step is by the operator performing an emergency shutdown. This is in case that things did not go well, so the operator is taking another safety precaution, that's putting it in shutdown. So these are 4 safety steps that could be taken. So again, when I know the 4 steps, I need to know, okay, what are the probabilities of those steps? So here are the probabilities. I'm going to calculate the failure rates, okay, or the occurrence rates, and it's written here. The event tree can be use quantitative data available on the failure rates of the safety functions. So we need to know the failure rate. We can also know the occurrence rate and know the opposite of that, which is the failure rate. For example, a loss of cooling event occurs, and there are 4 steps, right? 4 steps. And the first step, where the hardware safety function, which is the alarm, it fails 1%, okay? So we are going to assume that it fails only 1%. And sometimes we already know the failure rate, right? Sometimes we already know the failure rate, which maybe it's 0.04. But in this case, we are going to say that the possibility that this alarm will fail, telling us that they have a high temperature, is 0.01. Now we go to the second part. So assume the operator will take action, right? But how many times he will take action if there is an alarm? So we are assuming that in every 4 times he takes 3 times actions. So one time, like, he just misses that out. So 3 out of 4 he's going to be taking action, and this sounds good, because above 70% usually the operator is attentive. More than that, 90%, this is usually not applicable. Only when you go to civil aviations, where they need this kind of a lot of concentrations of having planes coming in and planes going out from this runway, and that is really because it's very dangerous. It has a lot of lives, depending on just minute or less than a minute. So that the attentivity there is really very high. But here we could consider that 3 out of 4 is good. In this case, we are talking about what? The operator noticing that there's a high temperature, and then the operator is fixing this by changing the coolant flow. Each one we are going to consider 3 out of 4, which is 0.25. 0.75. 0.25 is the failure per demand, right? So it is 0.75 here. 3 over 4, it is his occurrence success rate, so the opposite is 0.25. Finally, it is estimated that the operator shuts down the system. So if it happens that things really went bad, the operator will shut down the system most probably, of course, because he already went through this missing thing alarm, and now he's getting it, and now he knows that the temperature is going out, and the alarm's just passed, right? Like, and things are still going up. He's going to take an action, and that's about 9 out of 10. So the failure rate is 0.1. So 0.9 is the success rate, 0.1 is the failure rate. So what do we have here? So just to go and look into the details of it. So that is the tree diagram. That is our tree diagram. So what do we have? We have a high temperature alarm alert operator. So we already said that this is 0.01, if you can recall, okay? It was 1%. That alarm, it will only fail 1%. The operator will notice the high temperature, 25%. A failure, the 25% failure. The operator restarts the cooling and he fixes the cooling rate, 25% failure, which is 3 out of 4. Shuts down a 90% good, but 1% failure. Okay? Or that it's not only failure, you could call it that it will not occur. He's not going to do that. Okay, so we have 0.01, 0.25, 0.25, 0.1. So what do we have here? We have an initiating event, which is the loss of cooling, which is once per year. Okay, what will happen if we have loss of cooling? So we are going to start with this, saying that, well, we have a high alarm operation here, which is 0.99 and 0.01. Okay, 1% it will fail, and 0.99 that it will not fail, which means that we are saying that the top line is the success one, the down line here, the bottom line, is the failure one. So if you go continuing, this is the success, this is the failure. If you go here, this is the success, this is the failure. If you can see here, we have success. We need to stop here for failure, but this doesn't count because things are in success, so there is no shutdown, right? So it will go just straight on. So there's no safety thing, that precaution that we have here. But in this case, there's a possibility here that if he restarts cooling, there's a possibility that this would fail, and if it fails, it goes like that. Okay, and the ADE are just this A initiating, and D is the not cooling, and E it shuts down. So this ADE event is the A, D. So this is the D. It starts from here, D, and E it starts that way. So that is the A. Sorry, the A, D, E. Okay. Why D from here? Because we have D, it starts from here, and we have E, it starts from here. So looking at AB, for example, so A failure. If do you have a success where the operator notices high temperature, so it will go for a success. Now what will happen? Because it notices the high temperature and the operator is restarting cooling, and it goes here to continue operation. Actually, this sounds like ABD for me, by the way, because there is an action here. There is an action here. Well, we could say that this is a success, right? There's no action here because we are saying that there's a success, and this is why it goes to continue operation. However, if there's no success, we need to split out, and once splitting out, you're counting this action here, which is ABD, and ABDE, of course, if we are taking the action of the second one. Okay, so the top one is the success, the bottom line is the failure. What do we have else? So we have like 1% failure, 0.99, and then what should we do? So nothing is happening here. Because the alarm went on, and you're taking all the probabilities in this tree. Okay, so you're taking the probability if this is a success that the alarm is on. So you don't need now the operator to take in on an action. So he's going to take an on action. That is a success, right? That is a success. But if there's a failure, we need to multiply it by the failure. And this is what we have. The operator restarts cooling. So how did this number come on? The 0.7425. 0.7425 is 0.99 multiplied by the number that we have here. Okay, 0.99 into 0.25 is 0.7425, and the failure time 0.99 to 0.25, you subtract it by 1, you're going to get, 0.99 to 0.25 is failure. This is 0.25 failure, so you will get 0.2475. Okay, so that number here that we have is 0.99, and I don't know if I can write this. So this is like so this is 0.99 multiplied by 0.25. Okay, so we go again and zoom in. So that is 0.99 to 0.25 is 0.2475. The rest is the success thing where you continue operation. Now, if the operator restarts the cooling, and still things fail, okay, fail, that means you need to multiply it by 1.1, so it becomes 0.02475. Okay, and the rest, which is 0.2475 minus this number, is that 0.2227, where it goes to shutdown. Okay, so let's take something else where this is the initial thing about if it fails, the alarm fails, it's 0.01, and now if it fails, what if the operator does not notice the high temperature? So as another failure, so it's 0.25, this 0.25 multiplied by 0.01, you get 0.0025. If the operator also fails to restart the cooling, so you're talking about the 0.25, here's the 0.25, multiplied by the 0.0025, you get 0.000625. Now, if the operator also fails to shut down, this is like impossible, right? And this is why you have a very low number. So you multiply the failure, which is 0.1 here, into this 0.0625, you get this number here, right? Of course, if it fails, then things are bad. So this X means that this is bad, okay? And this is like a success, which is just without an X. Now, if I want to calculate the shutdown, all the shutdown numbers, the shutdown here, the shutdown here numbers, we will see that this the probability of having shutdowns is 0.225 occurrences per year. Okay, so every 4 years I'm going to have one shutdown, and that is the usual case if you think of it in real life. What about runaway? Runaway, that means things that just run away without a shutdown, everything is a disaster. How much that is 0.025 occurrences per year. Okay, so if you multiply this by how much? Oh my god. If you multiply this by 1 to 2.5 or 4, which is so that is talking about it could happen maybe 25 times per 1,000 years. Okay, 100 years is 2 times. Okay, and 100 years is only 2 times. Do you imagine that 100 years? It's more than the life operation of that plant. You already have a shutdown as well. So you already can see that we are saying that it will never go to runaway. That was the way of how to do your event trees. I know it was little confusing because you have a lot of numbers here and there. There's some kind of assumptions that we also need to include in our problem, and this is what makes it sometimes for you think that this is difficult. It's not difficult. You need to understand the process. But talking about the numbers, how many faults per year, what are the assumptions, consider this to go back to your experience when you go to the industry, or it will be given to you if you're talking about as a student, so you're going to have these numbers. Things that are very obvious, which you can get from the tables for alarms, for valves, this may not be given to you because you can get them from the tables. Okay, I know that they're not much really related because they are really faults per year in the table, but you still can use them. Fault trees, so now we are going to go to fault trees. So it is like a more like not an inductive method rather than the deductive method. Okay, so you're not getting into something and seeing what is happening. So fault trees, Actually, it came from the aerospace space industry, where it was used very extensively by the nuclear power industry to qualify and quantify the hazards and risks associated with nuclear power plants. A fault tree for anything but the simplest of plant can be really large. So we are saying that a fault tree is a very large thing. I mean, and because it's very large, even for the simplest plants, it's still very large, because it will have thousands of events. And because of that, we use computers. Okay, we use computers to do that. So we cannot really do it really by hand. I mean, it's just learning process where you do it by hand, but things that are then put into computer, because there are a lot of numbers and probabilities. It's just very confusing, and you're going to have a lot of human error in doing that, and it takes just a lot of time. So fault trees are deductive for identifying ways in which hazards can lead to accidents. Now, we are not going through the series or sequence of events. We are talking about that I am expecting what are the accidents. I'm going the other way around, sorry. It's more deductive. How the hazards can lead to the accidents, okay? And then I can go backward. And this approach with a well-defined accident or top event and works backward towards the very scenario, okay? It is something like the what if. So it's not the what if, sorry, because the what if saying that what if the pressure goes up. No, it's like that. The temperature in the reactor, the reaction in the reactor runs away. We have a runaway reaction. Why? And then you're going to put the reasons, and then each reason you're going to say why, and you're going to get more reasons for every part. The runaway reaction, because you have a runaway reaction in this system here. Why? It is because that the cooling stopped. The cooling stopped maybe because of the pump not working. The pump is not working because of, and so on. So you can see the way that how we are trying to see things. For example, if you have a flat tire, okay, a flat tire, and here if you just see this rectangular, that means it's like intermediate event. That means intermediate means that that there could be more than one reason for why this is happening. Okay, this flat tire. It could be because the tire is bad, right? So we start with the top event always with the rectangular, because it is an intermediate event. And then this flat tire that you have, it could be because of a tire failure. You did not change it. Whatever tire you hit a pavement on the way. There could be many reasons. So that is why it is a rectangle. It's an intermediate event. Something like happening more than one thing, but you can just mention it as tire failure. Or road debris, like a nail. Definitely a nail would cause to flat tire. Okay, so that's why it is a circle, like it's a direct relation that we know that it happens. So flat tire will happen because of road, nail, or debris, anything like a nail, or a tire failure. Now you can see the shape is like that. So this is or, because and will look something like that, and that's straight here. It is straight from this side. So it's like that, okay? It is like that. It's oval from the top, the same, but it is flat from the bottom here. So here, this or that. Now, why do you have tire failure? It could be because of poor tire, or it could be because of a defective tire. Okay, so now I'm building my fault tree. And actually fault trees, it can be more complicated because it has AND gates, as I showed you here, OR gates, inhibit events, basic events. These are the circle basic events. This is the rectangle intermediate event. This is, if it's written here, if an event that cannot be developed further due to the lack of suitable information. So you don't know what to do, you just stop, there's undeveloped event. Sometimes you have external events that's coming into being. That is an event that is a boundary condition to the fault tree. And sometimes you need to go to another paper because you don't have a space on your paper. So you put these kind of connections for yourself. And that was the way of fault tree. There are lots of calculations fault tree. We are not going to go to the details of the fault tree because it needs a computer to solve, and it's very very confusing. But we need to understand how to build those fault trees. So not towards the numbers, but we need to go through the concept. So for example, we have here before the actual fault tree is drawn, a number of steps we need to do. Okay, so what are the things that we need to do before we draw it? First, we need to define very clearly what is the top event. The top event is the flat tire, or for example, high reactor temperature, or the liquid is too high. So that is the first thing that I had, or the explosion of the reactor, fire in a process. But explosion of reactor, fire process are usually too vague. So it's not very specific, because explosion of reactors, like, there are huge number of events, of detailed things that I should mention for why this reaction, the explosion of reactor happened. Okay, so the second step, after knowing what's the top event, we define the existing event. So what conditions are sure to be present when the top event occurs. Okay, so for this to happen, what should have happened? Why did it happen? And then we define the unallowed events, so things that we are expecting or we don't expect. But there's one thing here: the things that are existing events, we are going to include them. But sometimes we don't want to include, but we are going to write them on side. What are the unallowed events? For example, what are the unallowed events that are unlikely or not under consideration at the present? Why? It's like wiring failures. So you don't want to mention like wiring failures because that could be like hundreds of things, of reasons that takes us to nowhere. Or lightning, barq, tornadoes, hurricanes. I mean, these things are like crazy if you try to include that. This could have happened. Now you're studying. It's not that it had happened. Okay, you're studying why the high reactor temperature is going to went high, because we would expect that we will have a tornado one day. So it's like you're saying that why one of the reasons we could have a tornado. Why could we have a tornado? Oh my God, because I don't know what. So imagine that if you go through these details, it doesn't happen, right? It doesn't work, I mean, through fault tree analysis. And then of course you're going to consider putting the physical bound of the process, because this is one of the things, like physical bound, like the cooling rate has a certain maximum flow rate in that pipe and the power of the pump. So that is a physical bound. You need to consider this to see that why it is not catching up with the exothermic reaction that is running away. What components are to be considered in fault tree? Okay, they define the equipment configuration, what is the maximum pressure that the equipment can withstand, what is the maximum level, what are the maximum flow rate in that valve. Okay, define the level of resolution. Okay, which means will the analysis consider just a valve or will it consider the valve components? So we need to be very clear. Are we talking now more about the valve or the valve components? So just to know where to concentrate. And after, what you're going to do, you're going to start and draw your fault tree. So that's it. You're going to start your fault tree, where you put your basic, the circle ones, the intermediate things, that events that you have, and there could be or depending, and gates. It could be happening in parallel, or they happening together. Both events are happening together for that thing failure to happen, and so on. So an example here for 12.5, consider again the alarm indicator and emergency shutdown system. So it's the same example because you're already having it fresh in your head. Draw a fault tree for this system. So the first step is to define the problem. So what is the top event? Damage to reactor as a result of overpressuring. So we are talking about overpressure within the reactor. And this is why the alarm goes on. But you already found that the reliability is high, right? The failure of those things that we had was too low. But now let's go and through your analysis, doing your tree of events to find what is the fault. What are the events that could lead to your fault? What is the fault? Overpressure. So existing event is the high process pressure. Unallowed event, failure of mixer, electrical failures, because if you don't have well mixed, you could have more pressure, which means more gases. Okay, if you don't have maybe electrical failures, control valve is not working well, or wiring failures, control valve is not working well, tornadoes, hurricanes, these are unallowed events. Physical bounds, the equipment, actually they have each one of them some bounds. Equipment configuration, we need to write them. We have alarm, solenoid valve, reactor feed flowing. Level of resolution, we are talking about the equipment. So my main concern is the equipment. So I don't want to go and talk about the valve and forget about what I'm trying to talk about. And sometimes it happens, you talk with a person about a certain problem and then you start discussing something else other than the problem, and you're just deviated away from finding a solution to the problem. So what do we have? You have something like that. So overpressuring of reactor, that's the top event. And these are the numbers that we already obtained before, that the probability failure rate and the reliability. We already obtained those numbers. And we have an AND gate here, which means that this high pressure of reactor will happen. Okay, I mean, not the overpressuring of the reactor will happen if the alarm fails and the emergency shutdown also fails. Because if this does not fail, the reactor will not go to a high overpressure, but it will go to overpressure if the alarm fails and the emergency shutdown fails. Now, why does the alarm fail? It will fail for two reasons. If the pressure switch fails or the pressure indicator light fails, okay? So sometimes the switch is working but the light is failing, so you don't know that there's something going on, even that the switch is working. The shutdown will happen. Why? If the pressure switch 2 fails or the solenoid valve failure happens. And by this, what you're getting, we are getting the probability and reliability for each piece here, okay, for each one of them. Rather than multiplying, for example, we multiplied 0.87 to 0.96, right? To get our number here. This R here, if you can recall this, right? And then you're having these two in parallel, so you multiply the P's. This P multiplied that by that P. So I'm just trying to refresh your memory about what we have taken. So now, knowing the probabilities and the reliability of each system here, all what you need to do is do your calculation here. I did not show the calculation here, so let me see if I have it in 12.5. Well, we have the calculations, we have those numbers here, and actually these calculations are used to identify the minimal cut, where we do have the minimal cut. And I did not include the minimal cut, and I will just include it as a concept. I just recall what I have said, that we will not go through the numbering part here because it's more computerized and it's a bit complicated for how to calculate this. We already have the numbers, we have the answer here, right? Because we already calculated it by hand. But now, talking about which one of these could contribute to this most, okay? Did you get what I'm trying to say? So which event which contributes to this most? Now, think which one contributes to this most. That is where the part that we may not cover, and that is called the minimal cut, okay? And the concept of it, the simple concept of it is that saying that if I have less events causing this, I will consider that this is to be my minimal cut, okay? My minimal cut. And this is where we have talking about the minimal cuts. So once the fault tree has been fully drawn, a number of computations can be performed, and one of those computations is determining the minimal cut sets. The minimal cut sets are the very sets of events that could lead to the top events. So you're going to the smaller events till we go to the top event. In general, the top event could occur through a variety of different combinations. So the top event here could happen because of this line here, or it could go through this line here, or it could go through this line here, or it could go through this line here, right? So what I'm trying to say here, these are the possibilities. Well, I said this line here, but here we have an AND gate, so it's not only this, this needs to happen with this at the same time. So it's like both of them. So what do we have here? We are trying to determine the minimal cut set. So once the default tree has been fully drawn, we are what? We are putting the computations that we need. Okay, great. So what are the different unique sets of events that we have that lead to the top event? So we are calculating now. Finally, that is the solution. There's some kind of details that I need to mention here, and I'm going to mention them very quickly in a moment. So looking at example 12.6, it's the same example that you just are talking about, and this is where you start building and saying that where it could happen because of A and B, okay, and then we are replacing based on the details that we have here. For example, logic gate A has two inputs, one from B and the others from C. Because gate A is an AND gate, gate A is replaced by B and C. So you remove A and put B and C. Why did you remove A? Because this will happen because B and C. So you have two like columns here. And then you go to B. What will happen? When will B happen? B will happen if I have 1 or 2. Okay, you have 1 or 2. 1 will C happen. C will happen if I have 3 or 4. 3 or 4. And then going through the details, finally we replace that's the final part, gate C in the second row by its inputs. And that generates just the fourth row where we are talking about the possibilities here, right? The possibilities, the cut sets that we have. We have 1, 2, and 3, 4, and 1, 4, and 2 and 4. So these are the possibilities. We have 1, 3, 2, 3, 1, 4, and 2, 4. So you have all the possibilities that could occur. Of course, sometimes it could be a different form. It could be like 1, 2, 2, 1, 3, 3, 4, and so on. So going back, these are the arrangements that we have. So we are saying that the possibilities that we could have, let me go back, 1, 3, 2, 3. So 1, 3, 2, 3, 1, 4, 2, 4. So these are the possibilities that things that can happen. This and that happens, or this and that happens, or this and this happens, or this and that happens, okay? And now, just by saying and explaining, I'm sure that you have wires in your head getting inside each other, right? So not to get these wires getting inside each other is enough for you to understand the concept of the minimal cut sets, because we are not going to take problems into these details because it's computerized and it's enough for you to understand the concept. Now going to the final parts of our chapter, those who studied process control from Seaborg's book, I think chapter 10 or 11, I can't remember which chapter, they cover this part here, where you have layers of protection to lower the frequency of a specific accident. So what is your protection? First, you're going to have a design, which is inherent safety, it's inherited. And then you have your control systems to have everything in its place. Temperature, pressure, level, everything is controlled. But if things go out of action and control, you have alarms and some human interventions. Now, even those people, alarms and human taking action to when they see an alarm, they put things off and on. If they don't take their intervention in place, then we have the safety instrument functions getting into place, right? It's automatically shut down systems and so on. But before shutdowns, could be some only instrument functions, and then you're going to have the relief devices, okay, the relief devices, and if not, and then you have the dikes. It's like a physical protection to your system, just not to lose your equipment, right? If you lose all your liquid, but it is within a big dike, hole, okay, so that you don't use your liquid and you don't have a lot of exposure to that liquid or those vapor exposures. And then you have your plant emergency response and community emergency response to the people around. So this is like different layers, and these layers, of course, you need to, as I explained here, you need to have the idea of safety actions through all the layers, okay, through all layers here. So you identify a certain sequence and you go with the scenario, and you start with one event and another event, and you go through all the protection layers and you put all the probabilities on that layer. So you go from one place to another and you see the probabilities, the frequency, the consequences, and of course you will have the risk, if it is acceptable or not acceptable, by looking at all the layers together, And these are just an example. For example, frequency from literature per year. And this is the frequency range for any pressure vessel residual failure. So now this is very specific. A certain failure in a pressure vessel, a certain piping leak failure per year. And these are the numbers that we have. And an example of a value chosen. Now what does the LOPA? LOPA just takes an average of these numbers. So instead of 10 to the power minus 5 to 10 to the power minus 7, it takes an average to 10 to the power minus 6. So the LOPA is also a number, and we always try, as in engineers, we use numbers just to quantify things, and then we look at the quality part of it. Okay, and these are the actions that we said. We can use a dike, we can use a drainage system, an open vent relief, and so these are the what they call the passive, the protection layers. I forgot the I is for what. We're going to look at that in a moment. So you're going to try to have this passive layer to take action. I think the inspection passive layers or something like that. And these are the probability for the failures and demand. It's called PFD. I know it's not the plug flow diagram, something different here. And what do we have? We have PFDs, the probability for failures and demands for passive inspection protective layers. And so what do we have here? These are the comments that we have for passive IPLs. Reduce the frequency of large consequence. So don't have a widespread spill, because the dike will overfill. It will not cover up all that, right? If you have a drainage system, reduce the frequency of large consequences to have this drainage system. It is spilling by itself, right? Or spilling from a tank overfill that this drainage system will not handle. Or open vent, of course, it is preventing any pressure. It is trying to do this thing. But we should be careful that this open vent should be also withstanding this overpressure. Fireproofing. So fireproofing is good because it will reduce the heat input and provides additional time for depressurizing. So it is proving, it's a proof not to have fire, okay? But we need to make sure that it is in place to prevent this from happening. So these are the IPLs that I have. Okay, these are the IPLs that I have, and these are just the numbers of those probabilities for failure and demand for what I have as IPLs to recover that from us. And if you see from industry and CCPS, it's just a different center for chemical process safety where it has a different number. And just considering that I just want to use one number rather than two numbers. Okay, and that is for relief valves, rupture discs. So all these are the protective layers. Okay, all these are protective layers. So just to go to the concept of the PFD, it is used when designing emergency shutdown system. So when we want to do an emergency shutdown system, or sometimes called safety instrumented functions, SIFs. We want to achieve low probability of any failure demand, okay? And why? How to do this? We can do it through many things. We already mentioned many IPLs, but we can do this by having redundant sensors. And by the way, when you put redundant sensors and redundant control elements, you will have OR gates, and you're going to see that your reliability is going to be high through your calculations. using multiple sensors, testing the components at specific intervals to reduce the probability of failures. So it's redundant, using more than one sensor. If one sensor doesn't work, the other works. You're testing them just to make sure that they are working, right? Because if you don't test them, and then, for example, you have a redundant sensor. If you don't test your redundant sensor, maybe your redundant sensor, you did not put it on for 2 years, now it's not working. So when you're trying to use it, it doesn't work. So you need to test, right? You need to test. And of course, sometimes you also need to test like a shutdown system just to make sure that it's working as well. Okay, so there are 3 integrity safety levels that are accepted in chemical process for a major shutdown system. So this is one integrity level, that's another one, another safety integrity level. What are they? These are normally implemented with a single sensor, a single logic solver, and a single final control element, and they require periodic proof testing to know that all of them will work. A second layer, of course, you will expect that you have redundancy. A second layer, fully redundant, including sensor, logic solver, and the final control element, and of course needs some testing. What is the third layer? The third layer, typically fully redundant, and the system requires careful design and frequent validation tests. So it is redundant and it has testing as well. So the first one, no redundancy, only testing. The second one has redundancy. The third one has redundancy and testing. So that's the whole part that we have for risk assessment. And I think so that you had a good idea of the risks. So those were the risk where we calculate if it has a high risk, if it has high frequency, or it has a high risk if it is dangerous. And then we talked about the probability theory where we calculate the failure rate, and based on the failure rate we calculate the reliability, and the probability failure is just 1 minus the reliability, and we have taken an example for that. And later we have went through the event trees, where event trees is more like an inductive process. And what we meant by inductive, that means we have the failure that we have here, and we are looking at the action. So we're going inside rather than going outside, right? We are going inside. We are not seeing that what caused. This is the deductive. This is where the fault tree analysis. The fault tree analysis goes from here. Well, it says that what caused this increase, what caused this cooling to stop, this cooling flow rate to stop. So you do your tree here, okay? You do your tree here, putting the AND and OR gates and so on, right? And this is what you're going to do. But that's the fault tree analysis. So that is the fault tree analysis. Now for the event tree, no. If this cooling rate or flow rate stops, what should I do? If it's successfully this person takes an action, we go up. If he doesn't take an action, this is the failure rate. And then if the operator did not restarts the cooling, going up. If he did not restart the cooling, going down. So this is like an inductive, going inside it and taking action. So that was the fault tree analysis, and we went through that and did some calculations. So that was the event tree. The fault tree analysis was that part here, and we said that we will know how to draw and have an idea about it, but we will not go through the details of doing the calculations to get them the cut point, because sometimes it's a bit confusing of how to get this minimal cut points, and this is done through computers, so don't worry about it now. And then we need, of course, to have a good risk assessment. We need to consider all layers from the process design till we get to the people who are sitting neighborhood to this industry, and we went through the details of that. So that's all for chapter number 12. Thank you very much. This is Dr. Bassam Al-Hamad. We covered chapter number 12, risk assessment, and from the book Chemical Process Safety. Thank you very much, and I appreciate your presence here. Master.